Hi, my name is Curtis and I'm going to talk to the numbers in the Fibonacci sequence. So this is Fibonacci and this is the sequence. How it works is you take the previous two numbers and sum them together to get the next one. For instance, 1 plus 1 is 2, 2 plus 1 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13 and so on. Now, the interesting thing about the Fibonacci numbers is that they appear a lot in nature. For instance, I googled up two pictures of petaled flowers and as you can see the numbers of petals on the flowers just happen to be Fibonacci numbers. Another interesting property, which is really cool I think, if you take the Fibonacci numbers, and as I've done, square them, so 1 squared 1, 2 squared 4, 3 squared 9 and so on, you can get an interesting little factor from them. If you sum up the square of the numbers, for instance, the first 3, 1, 1 and 4, you get 6, the first 4, 1, 1, 4 and 9, you get 15, and so on. There's a little, if you look carefully, within the 6, the 15, the 40 and so on, you can actually find the Fibonacci numbers. If you can't see them, if you take their factors, 6 is equal to 2 times 3, which is the third and fourth Fibonacci number. 15 is equal to 3 times 5, which is the fourth and fifth Fibonacci number, and so on. Now why is this the case? Why is it that the sums of the squares of the numbers is equal to the previous two numbers times together? Well, we can show this quite easily. If we take a box, a square, of length 1, and then we take the next one, so we've got both the Fibonacci numbers, then the next one will be 2, so we take a box of length 2, then of 3, then of 5, and then of 8. So now we've got a large rectangle made up of boxes of Fibonacci numbers. If we can consider the area in two different ways, and if they're the same area of the same thing, they must be the same area. So the first way to calculate the area of this is to take the sum of the areas of each box. So the area of the box with length 1 will be 1, the one with length 2 will be 4, and the one with length 8 will be 64. We add those all together, that's what we end up with. We end up with 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared. So that's one way of calculating the area. The alternative is to do the length times the height. So we do this by taking the length on the bottom, 5 plus 8, and timesing it by the height, which is 8. And as you noticed, when we're working out the length along the bottom, 5 plus 8, all we're doing is working out the next number in the Fibonacci sequence, because we're taking two Fibonacci numbers next to each other and adding them together. Hence it comes up with 13, which is a Fibonacci number. So that's why 1 squared plus 1 squared, and so on, is equal to 13 times 8. So if you take the sum of the squares of a number, it's equal to its number, original Fibonacci number, times by its previous Fibonacci number. So if we take that shape I had a moment ago and draw a graph around it in a circular fashion, we end up with this really interesting pattern. And as you can imagine, we can keep going this with larger and larger boxes and larger squares. And this, like the Fibonacci numbers, which appear in nature, this shape also appears in nature. The most commonly known one is within sunflowers and snails. As shown, you can see slightly within there, if you follow a path around the sunflower, you can see that curve appearing. And as put on by the graph there, you can see the snail form that follows a similar pattern. And some people say there are many ways in the human body that this pattern also exists. That's my presentation on Fibonacci numbers. Let me know what you thought, and if you want to learn anything else about maths or any other topics, let us know. Thank you.